Hello, everyone. My name is Kenta Murakami from Panasonic Automotive Systems. Okay, thank you for participating in my presentation. So I'd like to talk about the newly upgraded Unified HMI today. Okay, before I begin my presentation, I will introduce myself briefly. I'm working for this company about for 4 years, and I'm always focusing on the graphic-related development, especially in display virtualization across multiple display like Unified HMI. And as Jerry-san introduced yesterday, last time in AMM, I was absent from it because of wedding ceremony. And that is, thank you very much. Thank you. That is the photo we are taken in the Kyoto temple. So we are wearing the Japanese kimono. That was traditional photos. And this is the World Expo in Japan. And this is a Germany pavilion. So that was great. So if you come to Japan, please go there. Okay, let's start my presentation. I have divided my presentation in 4 parts. First, I will explain what is Unified HMI, and next, I will introduce today's main topic, upgraded for Unified HMI. And next, I will introduce how to use Unified HMI frameworks in your environment. And finally, I will share the future vision of Unified HMI. So first topic is what is Unified HMI. And before that, I will introduce the background explaining why Unified HMI is necessary for automotive industry. As mentioned in some keynotes, SDV is one of the trends in automotive industry, and we are focusing on the multiple displays. In recent years, the number of in-vehicle displays has been increasing because many in-vehicle devices, such as meters or displays, are digitization and turned into displays. This trend creates a new demand for flexible application layers across multiple displays for automotive developers. However, if we want to develop this flexibility using existing framework, the development of ad hoc coordination for each system configuration is required, like this figure. There are many differences in the types of hardware and operating system configurations, such as how many SoCs are used or which display is connected to SoCs, or even in which operating system is running on it. These are depending on the car grades and the models, so it will significantly increase both time and cost for developing. And as a result, there is a need for a software-defined display framework that can be used across different car grades and models without depending on complex in-vehicle hardware and OS configurations. So to resolve these challenges, we developed a software-defined display virtualization platform named Unified HMI. This is based on Virtual GPU, and it allows for flexible layout control of applications across multiple displays, independent of hardware and OS configurations. When you develop application layouts with Unified HMI, you don't need specific modification for each application, so they can be used or on various car grades and models seamlessly, and you can continuously update them for the future car generations. Also, Unified HMI has already released as open source on GitHub and AGL UCB. So I will introduce how to access and use them later in this presentation. By referring to them, you can easily test Unified HMI in your environment. From here, I will introduce how Unified HMI realizes the flexible application layout controlling independent of hardware and OS configurations. Unified HMI consists of 2 main components. In the left side, remote virtual GPU, we called RVGPU, And the right side is distributed display framework we calling DDFW. In the left diagram, our BGPU can render applications remotely in different SoCs or virtual machines via network, even when different operating systems such as Linux or AGL or Android are running on it. In the right side, DDFW flexibly manages the layout of applications across multiple displays independent of hardware configurations, such as which SoC is connected to which displays. It is also possible to span across multiple monitors like these navigation applications, or it can be render applications on only a part of displays, like jellyfish application. By using these two frameworks, the concept of unified HMI can be realized. And the following describes these components in detail. Okay. From here, I will introduce how unified HMI realizes flexible application layouts independent of hardware. Sorry. First is RVGPU. RVGPU is a network extension of virtual GPU, which commonly used for GPU virtualization in virtual machines. In the diagram, there is a detailed graphic data flow by using RVGPU from launching an applications in the left side and displayed in the receiver displays on the right side. And the green box is showing the RVGPU frameworks. By using RVGPU, the virtual loopback driver creates a new virtual GPU device on the sender side, which device is a virtualized remote virtual GPU on the receiver side. And when an application is rendered using this device, the virtual loopback driver captures GPU commands generated by OpenGL ES command and transmits them to RVGPU proxy. And next, RVGPU sends these commands and the texture data to RVGPU renderer on the receiver side via network. Finally, RVGPU renderer gets them and render applications on the receiver monitor by using GPU on the receiver side. As usual data flow without using unified HMI frameworks. And the RVGPU also creates virtual input devices such as mouse, touch, and the keyboard. So if you touch the applications on the receiver displays, you can touch applications. Okay, next is DDFW. As shown in the diagram, DDFW maps multiple cockpit displays on a single virtual screen. When using DDFW with RVGPU, you can control the layout of applications across multiple monitors independent of hardware configurations just by placing application on a single large screen. And DDFW allows developers to controlling layout such as location, size, and the display order of multiple applications on the multiple displays. And all layouts can be managed by the same some JSON files, and the DDFW can control layouts referring to that JSON files. Recently, we upgraded this unified HMI architecture to support different operating systems more flexibly. First, I will introduce the abstract about what has been upgraded for unified HMI frameworks. In the previous architecture, in the left side, unified HMI depends on the Windows system to controlling layouts on the receivers. Therefore, if we want to support various operating systems, such as Linux, AGL, and Android, specific plugins for each operating systems are required in the old architecture. However, in the new architecture in the right side, unified HMI no longer depends on the Windows system, so it's possible to support various operating systems without specific modifications or plugins for each operating systems. Yes, this is abstract, and from here, I will introduce the upgrades in detail. And before starting the introduction, I will explain what is the Windows system and why previous architecture depending on it. Windows system is a fundamental component of the graphical user interface called the GUI that manages the display of applications on the computer monitors. Operating systems such as Linux, AGL, and Android have their own specific implementations for the Windows system. There are two main components for displaying applications on computer screen. First is the window manager, which controlling where and how applications are arranged on the displays by using their layout controlling functions. And the second is the compositor, which compositing the application surfaces according to the layouts provided by the window manager. Next, I will introduce how Unified HMI controlling the layouts and why it depending on the Windows system. First, when you run applications on the sender using RBGPU, it creates application surfaces on the receiver side for each application. And these surfaces can be controlled by the window manager in layouts and compositing in the same way as applications rendered without RBGPU. Then, DDFW can controlling layouts of their application surfaces using controlling layout functions provided by the window manager via UHMI plugins. So these UHMI plugins leads to the dependency on the Windows systems for Unified HMI. In summary, there are two challenges in the previous architecture of Unified HMI. The first challenge is that specific development for each operating system is required to control layouts with Unified HMI DDFW. Please watch the diagram below. There are three operating systems, Linux, AGL, and Android, and there are some plugins for each operating system. And if we want to control layouts by using Unified HMI, Unified HMI have to use these plugins for each operating system. So, yes. And the second challenge is that if the layout controlling functions are upgraded on each operating system, it will be necessary to modify Unified HMI plugins to accommodate these changes. And continuously supporting each version of multiple operating systems individually are high operational costs. In the upgraded Unified HMI, it directly controlling the layout of and composites multiple application windows on the RBGPU renderer directory. And as a result, it's possible to simplify dependency on the Windows systems. Please watch the diagram. There are two RBGPU proxies on the sender, and they are all connected to a single RBGPU renderer. And when applications are launched through RBGPU proxy, they are composited by RBGPU renderer on its own. And also, DDFW sends controlling layout commands to RBGPU renderer, and it arranges locations and positions of application windows on its own. So in this new architecture, RBGPU creates only one surface without dependency on the number of applications. And DDFW can control layouts on RBGPU without using functions provided by the Windows system. And as a result, it becomes possible to support various operating systems without any specific development for each. The window manager only needs to composite the single surface created by RBGPU renderer. So just like with other applications without using RBGPU. Oh, so sorry. Sorry. Okay. Okay, here I will introduce the example about how to run upgraded Unified HMI frameworks on AGL IBA applications, which is called Flutter ICS home screen, like this. And as mentioned in before slide, if you want to use upgraded Unified HMI, you should launch a single RBGPU on Flutter ICS home screen in the same way as usual applications. And you can run and arrange multiple applications on it without using AGL window manager like gRPC command. In the diagram, RBGPU renderer composites two GL Mark II applications and composites them on one surface, like the left diagram. And you can, if you activate the RBGPU renderer surfaces, you can see such these applications on the Flutter ICS home screens. And you can also change layers of those two applications or RBGPU renderer by using DDFW. And after that, if you and you can also activate other applications. That applications can render on RBGPU renderer surface, so you can use as usual applications. Okay, I will introduce our milestones regarding the upstreaming of these upgrades. We have already released the upgraded Unified HMI frameworks on our GitHub. And we are currently testing them in some environments and making improvements. So by September or sooner, we will start contributing to AGL UCB, and it's expected to be completed on November. And in December, we will give a presentation at Open Source Summit Japan about using the upgraded Unified HMI frameworks and collaborating with multiple operating systems such as Linux, AGL, and Android. And I will introduce the abstract of this demonstration in the later of this presentation. And next, I will introduce how to use the upgraded Unified HMI in your environment. And Unified HMI frameworks are released as open source on GitHub and the AGL UCB. So you can access it on this using this URL. The main source codes are on GitHub, and there are some README documents for each framework that shows the procedures of using them. And in April, Ito-san contributed to our operating OSS code, and he will become the first contributor to our Unified HMI frameworks outside of my company. So thank you very much. And we are always looking forward to your contributions or reporting issues, so please give it a try in your environment. And additionally, Unified HMI is a standard component of AGL, and if you obtain the latest AGL software, you can get some recipes for installing Unified HMI. And there is a recipe for building pre-configured images for using Unified HMI, and there are documentations in the AGL official page. And this may help you easily test Unified HMI on your environment by using AGL environment. Okay. Currently, we upgraded Unified HMI framework, but not AGL UCB yet. But you can easily test our upgraded framework to change the revision of Unified HMI frameworks. Okay, next, I will introduce how to use upgraded Unified HMI frameworks in your environment. In this scenario, use two Linux systems as the sender node and one AGL on the receiver side. And first, please run RBGPU renderer on the receiver in the left right diagram. And next, run RBGPU proxy and RBGPU WL proxy and applications such as GL Mark II ES2 Wayland on both receiver nodes. When connecting to RBGPU proxy and RBGPU renderer, please set correct IP addresses and ports as options. And after launching the applications is completed, please run the URL command to control the layouts of the two applications on RBGPU renderer surfaces. And when you execute these commands on AGL home screen, you can see the result displayed on your screen as shown in the figures below. If you want to change the layouts, modify some JSON files, and run the URL command again, you can easily change the layouts of these two applications on RBGPU renderer. Okay, finally, I will introduce our future vision. We are currently focusing on the following three activities to achieve a more flexible virtual display framework with Unified HMI. The first activity is enabling application graphics to render in and out between AGL and other operating systems like Android. And currently, remote transfer of application is only possible between AGL and Linux. But in the future, we aim to support transferring applications from AGL to Android and from Android to AGL, and we are now developing. The second activity is the future zonal architecture. In recent years, the evolution of high-performance computing has led to the consolidation of SoCs. However, due to the increasing number of displays and their physical arrangements, there may be cases where distributing the SoC is necessary. In such cases, by using Unified HMI to distribute rendering resources to lower performance zonal SoCs, we can enable flexible expandation of SoCs. This allows UI and UX development without worrying about application performance. And we are advancing development on this collaboration with our company, and we released some media. And the third is extension to more media, such as audio or video, and etc. Okay, in this demonstration, I will show you the future demonstration at Open Source Summit Japan. In this demonstration, there are three systems, AGL IVI and AGL IC, and Android Passenger IVI. AGL is running the AI agent applications, for example, Linux Penguin named Tax, is running on the AGL IVI. And its application can display AI connected to the navigation Navi applications, and he can introduce the way to next way. And the agent applications are it's important where the agent application is shown on the display. The agent applications on the best position for drivers without dependency on the operating systems and SoC configurations. And also, all the software used in these demonstrations are developed on cloud environment using vSkipchain, a solution from Panasonic, and we have a demonstration on the floor. Okay, I will summarize this presentation. First, I introduced the upgrades for Unified HMI about simplifying dependency on Windows systems. And second, it's possible to support various operating systems such as Linux, AGL, and Android without developing specific plugins. And finally, I introduced our future plans to complete the contribution of upgrades to AGL and the demonstration we are currently developing. Okay, that's all of my presentation. So thank you very much.
We have time for some questions. Any questions? Uh-oh.
Okay.
Are there any plans to do the same with Vulkan clients? So the platform seems to be dependent on replaying back EGL or GL commands. So if you were to have a Vulkan client, will you be able to do the same with it, to move it and to use the UHMI?
Sorry, one more, okay. Sorry, I can't understand. So
I'm saying that are Vulkan clients able to run on the UHMI platform? Vulkan.
Vulkan. Sorry, we are just now supporting OpenGL, and we are now trying to support Vulkan also.
So you're working on it currently?
Thank you.
Okay.
Thank you. Sorry.
Thanks a lot.
Any more? Go ahead. Oh, you didn't have a question. Any more questions? All right, thank you, Murakami-san.
Thank you very much.